Right, sorry, Corrosion Stream 2. Audio might be fixed. Why is my chat not connected? Right, sorry. So this is my Corrosion Stream 2. Sorry, I'm trying to fix the audio on my end. I think I had something muted. If you have questions about the Corrosion course, do put them in the chat or into the comments below this video stream. And I'll either answer them now in words spoken, or else I will answer them in descriptions in the comments below the video. If you have longer or algebraic questions, do post them in comments below the video, and I'll get to them in writing. If there aren't any questions that I can see in the chat, and I possibly can't see any in the chat because I'm not sure that's connected to my streaming software properly, then in that case I will just go through. Oops. I will in that case go through the one question that I had in the comments beneath the Corrosion Stream 1, and that was to do with galvanic potential. So question beneath Corrosion Stream 1. Oops. So I had just a simple description: what is galvanic potential, and a couple of ways in which it's used. So if you look at the second lecture handout, then you'll get to section 4.2 in the notes, and you should find that there's a discussion of a question in bimetallic corrosion. So this section 4.2 helps to describe what is galvanic potential, because this question includes includes an example, which is what happens when you have multiple reactions taking place on a single piece of metal which has a single surface potential, which is its galvanic potential. So you're asked to consider the dissolution of a bimetallic strip which has some zinc and some iron, probably on the other side, and it's all sitting in acid dissolving. So there's two different metals dissolving, and there's two cathode reactions, which are hydrogen evolution, and there's a possible cathode reaction which is iron plating out. So the way that you consider that is you could either try to simplify the problem algebraically and say that you think only one anode and one cathode dominate what happens, and you say there's effectively only zinc dissolution, zinc anode, and hydrogen evolution taking place on the iron cathode, but the hydrogen evolution taking place on the zinc is negligible, and you can also say that any iron dissolution or plating is negligible. So you simplify the 4 reaction surface to just 2 reactions, and you solve for a 2-electrode corrosion cell. The more exciting brute force way to solve this is that you say, okay, forget about the need to simplify so that you get a simple to solve nonlinear equation. Actually, there's no problem brute forcing this and say, what is the total current density travelling through this surface when you add up the complete Butler-Volmer equation for each of the 4 electrode reactions. So you can do this by brute force because the equation is quite simple for each electrode. So you just consider a few hundred different conceivable, plausible mixed surface potentials, volts against standard hydrogen electrode, and for each surface potential you just compute the total amount of anode current for, say, zinc dissolving or iron dissolving, and the total amount of cathode current for, say, zinc, hydrogen evolution on zinc or hydrogen evolution on copper. And all you do is a brute force nonlinear solve for the surface potential at which the net surface current density is 0, adding up all 4 processes. And that gives you a stable surface equilibrium. If the surface is not at that galvanic electrical potential, then there's a net charge imbalance, a net current imbalance, which will tend to either add or subtract charge to the surface until the currents are in balance and there's 0 net current. That's just Le Chatelier, that the ongoing net anode or net cathode process, if there is one, tends to go forwards until it opposes and reduces to 0 the thing that's causing it to happen. And the thing that's causing it to happen is that there's a net polarization of the surface away from the galvanic potential, where there would be 0 net anode or cathode. So in this graph you've got the red line and the green line are the 2 metal anodes. They have their equilibrium potentials where the current density through the surface is 0 for them, and then the 2 black lines are hydrogen evolution cathodes on the zinc for the dashed line and the iron for the solid black line. The blue line is just what you get by adding all of them up together, and that's pretty simple to deal with. So where the blue line gives you 0 total surface current density, that's the galvanic potential, and your criterion for does your metal act as an anode is simply that every metal which has an equilibrium potential, which is both of them in this case, which are more negative than the galvanic potential, are expected to act as an anode. Okay, so that's your graph for galvanic potential, and then there's just a couple of questions. What if you have an applied surface potential? Well, in that case, I wouldn't. If you have some impressed current corrosion protection system, what would you call the surface potential? I would call it an applied surface potential, not a galvanic potential. I would call it E for a surface potential, capital E, subscript applied, or subscript ICCP for impressed current corrosion protection. And let's see. Then your applied surface potential, if you applied in this system a surface potential using an external power source of minus 0.2 volts SHE, there would be a net anode current density on the surface of this metal. If you're applying the surface potential, there's no problem. You can hold the surface there using electronics. It's just that your power source needs to supply enough current for this net anode process to take place. Okay. I don't have any other questions in the stream. And anyway, I think this galvanic potential explanation is better looked at in the written comment below the corrosion stream 1. So, if you don't have other questions which are going to appear in the chat, then I will stop that stream there. So do post in the chat if you have other questions about this CET2A corrosion course. Okay, right. Thanks very much.